Welcome to ilectureonline. In this video, we're going to take a look at a dam in a general sense. Here's the dam structure. Here's the water behind the dam. Here's the front of the dam. Assuming that the front of the dam is straight like this, that's not always the case. Smaller dams typically are built like that. Very big dams sometimes have a parabolic curve here, but let's assume on this side we have a straight line. We have the middle section right here, and then we have the side of the dam which is facing the water, which is typically parabolically shaped like this. We can then take the dam and divide into three sections. The triangular portion section right here, the rectangular portion section right here, and the parabolic section right here, but it's all one solid piece of concrete. Then behind it we have the water. Here we can have that section of water that is pushing against the dam due to its weight, and then we have the pressure of the water which is pushing in this direction caused by the pressure in the water. And you can assume that the pressure in the water is like a distributed load, just like a load on a beam, changing in magnitude as you go further and further down into the water. Assuming that the water has a depth of 18 meters, notice the height of the dam then is 18 meters. This section here is 9 meters wide, this section is 6 meters wide, and this section from there to there is 10 meters wide. We could then take each section and assume it to have a certain amount of weight. Call this W1, weight 1 of the first section, weight 2 of the second section, weight 3 of the third section of the dam, the concrete portion here, and finally the weight of the water pushing down on the dam this way. We want to find the distance from the beginning of the dam right here to where these forces are acting. That's why we need to find the centroids. The centroid of the triangular portion is 1/3 the distance from there to there from the bottom, and 1/3 the distance from there to there in the horizontal direction. The centroid of the rectangular portion is easy to find. It's right in the middle, halfway between this point and this point, halfway between here and here. The parabolic section is a little bit more complicated. We can find the centroid of the portion of the dam right here, which is 1/4 the distance from the bottom to the top and 3/10 the distance from there to there. We also can find the centroid of the water portion right here, which is 3/5 the distance from there to there. That would be 3/8 the distance of 18 meters from there to there. But we don't need that to find the centroid, but it's a nice thing to know. Finally, the centroid of the distributed load due to the pressure is 1/3 the distance from the bottom to the top, so 1/3 the distance of 18 meters. Now let's find the centroids of these four portions of the dam, including the water. So the centroid for the first here, let's call it x of 1, is equal to, notice that if this is 1/3 the distance, that's 2/3 the distance, that would be 6 meters from there. So the first centroid is 6 meters. The second centroid would be equal to 9 meters plus this distance right here, which is an additional 3 meters. So it would be 9 meters plus 3 meters, which is 12 meters from, let's say, point A. Let's call this point A right here. So from point A in a horizontal distance, the second centroid is a distance of 12 meters in the x direction. The third centroid, x sub 3, that is equal to 9 plus 6, so 9 meters plus 6 meters plus, and here we see that it's 3/10 the distance of 10 meters. So it's 3/10 of 10 meters, which is 3 meters. That's a total of 9 plus 9, 18 meters. And finally, the centroid to where the water is at, x sub 4. Again, we add up the 9 meters plus the 6 meters, 9 meters plus the 6 meters, plus, now we're looking at 3/5 the distance from there to there. That's 3/5 of 10 meters, which is an additional 6 meters, which makes this 21 meters. So the centroids for x1 is 6 meters, for x2 is 12 meters, for x3 is 18 meters, and for x4 is 21 meters. Why do we need the centroids? We need the centroids so we can find the moment caused by the weight of the dam and the weight of the water on top of the curved portion of the dam, pushing the dam in a clockwise direction, which means that the reaction moment here at point A would be the same moment in the opposite direction to hold the dam from going down through the ground, so to speak, which of course won't happen, but at least it's the reactionary force of the ground pushing back and the moment relative to A pushing back against the moment of the dam. Subtracted from that, of course, is the moment from the pressure, which is actually in a counterclockwise direction, which opposes the moment caused by the weight of the dam. So those are the basic principles of how we take a look at how we look at the dam structure, how we divide it into segments, how we find the centroids of each segment, how we find the weight of each segment, depending upon, of course, the volume of each section. This would be a triangular wedge, this would be a rectangular shape, this would be a parabolic wedge, and the water also would be a parabolic wedge. So that's why we need to find out where the centroids are, what the shapes are like, find the areas, find the cross-sectional areas, and then multiply times the width of the dam to get the total weight of each of the sections. In the next couple of videos, we're going to show you some examples of how actually to utilize all this information to find things such as what are the forces of the dams on the ground below, what are the moments caused by the dam, what are the counter forces by the pressure of the water and so forth, and how does that play a role in the dam, whether or not the dam would stay in place or whether or not the pressure of the water will push the dam over. Typically, they built these dams thick enough, wide enough, and heavy enough so that the pressure of the water has no chance of pushing the dam over or breaking the dam. And we'll see that in the next videos. That's how it's done.